Hello there, and welcome. Tonight, we drift into the ancient and extraordinary world of geology, the deep memory of our planet written in stone. Long before stars were named or oceans had boundaries, the Earth was already alive, reshaping itself in silence. Mountains rose and crumbled, seas vanished and returned, continents wandered across glowing oceans of rock. The ground beneath you is ancient beyond imagination, and yet it is still moving, still breathing, still changing. This is the story of geology, a story of fire and water, of creation and collapse, of beauty that takes millions of years to unfold. Beneath every step, within every pebble, there are whispers of volcanoes, glaciers, and stars long gone. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the ancient earth cradle your thoughts. Let's begin. Earth's crust is thinner than you might imagine. If you could shrink the planet to the size of an apple, the crust, the solid outer shell we live on, would be no thicker than that fruit's skin. This idea feels almost impossible, yet it is true. The continents and ocean floors together form a layer that, on average, extends only about 30 kilometers deep beneath land and less than 10 beneath the sea. Beneath that lies the mantle, a vast region of slowly flowing rock that makes up most of Earth's volume and mass. The crust floats on this mantle like fragile rafts adrift on molten currents, carried and reshaped by plate tectonics. Mountains, valleys, and ocean trenches are tiny ripples on the surface of an enormous sphere of stone. Everything we know, every forest, city, and ocean, exists atop a layer so thin it could almost disappear in scale. Granite once flowed like molten rivers deep underground. Long before it hardened into the rugged stone we see today, granite was alive with heat. Deep within the Earth's crust, molten magma gathered in hidden chambers, moving like slow rivers of fire. Over millions of years, it cooled and crystallized into the familiar speckled rock that now forms the hearts of mountains. Each grain of quartz and feldspar once shimmered in a molten glow before solidifying forever. When you run your fingers over granite, you are touching the cooled remains of that ancient flow, frozen in time. Many of the world's great landscapes, from Yosemite's cliffs to the Scottish Highlands, were shaped by granite rising and solidifying below the surface. It holds within it the patience of the planet itself, a reminder that what appears solid today was once liquid light, slowly transforming beneath unimaginable pressure into something enduring and eternal. Diamonds can form in a heartbeat when conditions are right. Most diamonds take billions of years to grow deep within the mantle, born from carbon crushed and heated beyond imagination. But nature can be unpredictable. Under the most extreme pressures, carbon can rearrange itself into diamond almost instantly. These sudden transformations happen miles beneath the surface, where temperatures are hotter than molten metal and pressures exceed anything humans can replicate for long. When volcanic eruptions bring these gems upward, they travel through narrow pipes of rock called kimberlites, carrying a story from the depths of Earth's creation. Each diamond you see, no matter how small, once existed in darkness and heat so fierce it could melt steel. Whether formed slowly or in a geological heartbeat, Each crystal captures a moment when ordinary carbon became extraordinary. They are nature's perfect record of transformation, born from chaos and pressure, rising toward light through the very bones of the planet. Some mountains are still rising faster than your fingernails grow. Mountains appear eternal, but they are alive with movement. Deep beneath the surface, tectonic plates push and collide, forcing rock upward inch by inch. In the Himalayas and parts of the Andes, this slow collision is still lifting peaks faster than your fingernails grow. What feels solid is actually part of an endless cycle of uplift and erosion. Wind, water, and ice tear mountains down grain by grain, while forces deep below rebuild them in a rhythm that is played out for hundreds of millions of years. A mountain may seem motionless, but if you could speed up time, you would see it breathe, swelling upward as continents collide. The stone beneath your feet may once have rested on the ocean floor, carried skyward over epochs. These giants remind us that Earth is not still at all, but in constant motion, reshaping itself even as we sleep. Entire continents float like rafts on molten rock. The ground beneath us drifts on a hidden sea of molten rock. Beneath the crust lies the mantle, a region so hot that solid rock behaves like an incredibly slow-moving liquid. The continents rest on this mantle as enormous rafts of rigid stone, drifting across it through time. They slide, collide, and separate at rates of only a few centimeters per year, but over millions of years, those tiny movements reshape the world. Oceans open and close, mountain ranges rise, and entire climates transform. The continents we know are travelers, always in motion, though the journey is invisible to us. This slow drifting is what once united all land into the supercontinent Pangaea, and will one day bring the continents together again. Our planet is alive beneath its calm surface, and we are passengers on its vast drifting plates, carried across geological seas without ever feeling the motion. Earth's surface is constantly recycling itself through plate tectonics. Nothing on the planet's surface is permanent. The continents and seafloors we see today are part of an endless process of destruction and renewal, known as plate tectonics. Where plates collide, mountains rise. Where they separate, new ocean crust forms as molten rock wells upward. In other places, one plate dives beneath another and sinks back into the mantle, melting to become part of the Earth once more. Even the ground beneath the oceans is born, spreads, and disappears on a timescale of tens of millions of years. Every grain of sand, every cliff, every volcanic plain is part of this great planetary cycle. Earth is the only world we know of that recycles itself so completely, using the slow power of heat and gravity to keep its surface young. The planet's skin is never truly still, but forever shedding and remaking itself in quiet, graceful motion. The Himalayas are still growing taller every single year. High above the clouds, the Himalayas continue to rise. Their growth began around 50 million years ago, when the Indian plate collided with the Eurasian plate, crumpling the crust like folded fabric. That collision is still happening, pushing the mountains upward by a few millimeters each year. The peaks may appear timeless, but their summits climb steadily toward the sky, even as wind and glaciers carve them down. Every tremor in the region, every deep earthquake, is a whisper of that immense pressure still at work. These mountains are not relics of the past, but the living result of an ongoing collision that began before humans existed. The same collision that built Everest continues to reshape the land beneath millions of people. In their silent rise, the Himalayas remind us that Earth's power is patient, relentless, and always in motion, sculpting continents as easily as clay. Continents drift as fast as your hair grows. If you were to measure the movement of a continent, it would advance about as quickly as your hair lengthens in a month. Yet over geological time, that small pace reshapes the entire face of the planet. Continents slide on top of the mantle, carried by convection currents deep within Earth. The Atlantic Ocean grows a little wider each year, while the Pacific slowly shrinks. In millions of years, familiar maps will be unrecognizable. Africa will move closer to Europe, Australia will edge north, and the continents may one day merge again into a single giant landmass. This slow drift connects the fossils of ancient creatures found oceans apart, and explains why mountain ranges on separate continents share the same origins. The ground feels solid, but it is part of a grand, restless voyage that has never stopped since the planet was born. The ocean floor is younger than most of the continents. Beneath the waves lies a hidden world in constant renewal. While the continents hold rocks billions of years old, the seafloor is surprisingly young. Along mid-ocean ridges, molten rock rises, cools, and forms new crust that slowly spreads outward. As it drifts, it eventually sinks back into the mantle at deep ocean trenches, where one plate slides beneath another. This recycling means no ocean crust lasts longer than about 200 million years, a fleeting moment in Earth's long history. The continents, by contrast, are ancient survivors that have floated above the cycle of destruction. If you could see the planet's surface over time, you would watch the oceans form and vanish like the rhythm of a breath. The seafloor is the planet's heartbeat, renewing itself endlessly, a reminder that even the deepest, darkest places on Earth are alive with motion and change. Magnetic stripes on the seafloor record Earth's ancient flips. Across the vast plains of the ocean floor, the rocks are patterned like a barcode. These alternating magnetic stripes mark times when Earth's magnetic field reversed direction, with north and south swapping places. As new crust forms at mid-ocean ridges, minerals within the lava align with the planet's magnetic field before they cool and lock in that direction. Millions of years later, another reversal leaves the next band pointing the opposite way. By reading these stripes, scientists can trace the history of magnetic flips stretching back tens of millions of years. This discovery was one of the keys that proved the theory of plate tectonics, showing how the sea floor spreads outward over time. Beneath the oceans lies not chaos, but a perfectly ordered record of the planet's invisible forces, written in stone by magnetism, heat, and the slow pulse of geological time. Rocks can actually become magnets after cooling from lava. When molten rock cools on the surface of the Earth, something extraordinary happens. Tiny particles of iron and nickel inside the rock align themselves with the planet's magnetic field, like invisible compass needles. Once the lava cools and hardens, those magnetic directions are locked in forever, preserving a record of the magnetic field's orientation at that moment in time. Scientists study these natural magnets to map the shifting history of the Earth's poles. Every reversal, every wandering movement of magnetic north is captured in stone. frozen as the planet's molten skin solidifies. These magnetic fingerprints are part of how geologists proved that continents drift and seafloors spread. In every volcanic rock lies a silent record of Earth's magnetic pulse, whispering clues about ancient directions and the invisible forces that shape the space around our world. The planet's memory is magnetic, written in the iron heart of stone. Every volcano on Earth connects to a hidden magma chamber. Far below the surface, each volcano has a heart that beats with molten fire. These underground chambers of magma are vast reservoirs of liquid rock, feeding eruptions that can reshape landscapes and change climates. Some chambers are small and shallow, others immense and deep, reaching far beneath the crust. Inside them, crystals form, gases rise, and pressure builds until the rock above can no longer hold it back. Then, with staggering power, the chamber vents its fury through cracks and vents, pouring lava and ash across the world above. Between eruptions, these reservoirs remain hidden, slowly refilling and evolving. Modern technology allows scientists to glimpse their shapes using seismic waves, like ultrasound for the Earth. Each volcano is part of this deep, breathing network, a reminder that beneath calm fields and sleeping mountains, there are vast, glowing worlds of molten stone waiting quietly below. Some volcanic eruptions last for hundreds of thousands of years. Not all eruptions are sudden, explosive moments in time. Some are patient and relentless, flowing for ages beyond imagination. When mantle plumes release massive amounts of magma, the result can be a flood basalt, a vast outpouring of lava that continues for hundreds of thousands of years. These eruptions can bury entire regions beneath miles of solid rock. The Deccan traps in India and the Siberian traps in Russia are enormous relics of such ancient fire. During their reign, they released enough gas and heat to alter the planet's climate and change the course of life itself. Standing on one of these hardened lava plains today, it is hard to imagine the molten rivers that once stretched to every horizon. They remind us that sometimes Earth reshapes itself not with explosions, but with the slow, unstoppable rhythm of fire spreading endlessly beneath the open sky. Basalt covers most of the ocean floor in dark, dense layers. If you could walk across the bottom of the sea, every step would land on basalt, a dark, heavy rock born of fire. It forms when molten material from the mantle erupts along mid-ocean ridges and cools quickly in contact with seawater. The result is a vast, unbroken crust stretching across the ocean basins like the planet's armor. Unlike the lighter rocks of the continents, basalt is rich in iron and magnesium, giving it its deep color and weight. Its solid layers continually renew as the seafloor spreads outward, while old sections sink back into the mantle and melt again. Each square inch of the ocean floor has been part of this endless cycle of creation and destruction. Beneath the waves, basalt holds the history of Earth's most patient movements, layer upon layer of cooled magma, forming the quiet foundation of the world's oceans. Pillow lava freezes in shapes that look like underwater balloons. When lava erupts beneath the ocean, it cools so fast that its outer layer hardens instantly, while molten rock still pushes from within. This strange process creates rounded shapes that resemble pillows or bubbles stacked upon each other. These smooth, bulbous formations, called pillow lava, can cover entire stretches of the seafloor. Each pillow is a snapshot of fiery motion frozen in an instant, showing how molten rock interacts with cold seawater. When explorers find pillar lava on land, it tells them that the area was once deep underwater. The sight of it is eerie and beautiful, as though the stone itself still remembers flowing like liquid before being sealed by the chill of the sea. These shapes are geological sculptures of time, proof that even in the dark, crushing depths, the planet's creative forces are always alive and at work. Obsidian is volcanic glass, cooled in an instant. In moments of explosive eruption, lava can cool so rapidly that crystals never form at all. The result is obsidian, a natural glass that gleams with dark beauty. It is smooth, sharp, and reflective, formed when molten rock meets cold air or water and solidifies almost instantly. For thousands of years, humans have prized it for its perfect edges, crafting blades, tools, and ornaments. Yet behind its mirror-like surface lies a story of extreme change. Molten fire arrested mid-motion. Heat transformed into fragility. Obsidian breaks easily, but along the break, it reveals stunning curved patterns called conchoidal fractures, as if each fracture remembers the flow of the original lava. This gassy rock stands as one of geology's most dramatic contrasts. Born in violence, yet perfectly still, fragile, yet ageless, a piece of fire caught forever in the stillness of stone. Some rocks preserve bubbles of Earth's ancient atmosphere. Trapped within the tiniest hollows of rock, scientists have discovered microscopic bubbles of air that have survived for millions of years. These preserved pockets are like time capsules, sealing the chemical signature of the atmosphere from ages long past. By studying them, researchers can learn what gases once filled the skies, how much oxygen existed, how much carbon dioxide warmed the planet, and how volcanic activity or life itself changed the balance. Some of these bubbles formed in cooling lava, others within sediments or ice. Each one contains an echo of an ancient breath, a ghost of the air that once surrounded early forests, giant reptiles, or even the first life to breathe. To hold such a rock is to hold a fragment of vanished sky, a delicate record of the ever-changing air that connects all living things across the long history of Earth. There are mountains higher than Everest hidden beneath the sea. Far below the surface of the oceans lie mountain ranges that dwarf the world's highest peaks. Along the mid-ocean ridges, immense chains of volcanic mountains stretch for tens of thousands of miles, rising higher from their base to their crest than Everest does above sea level. These submarine ranges are mostly unseen, shrouded in darkness and immense pressure. Yet they are among the most active regions on Earth. Lava continually emerges from fissures, building new peaks and valleys in slow, steady motion. The tallest of these hidden giants, such as Mauna Kea when measured from its base beneath the sea, surpasses even the great Himalayan summits. They are reminders that much of Earth's beauty and grandeur lies unseen beneath the waves. Vast, silent kingdoms of rock that grow and shift in darkness, shaping the world from below without a single glimpse of the sun. Earth's deepest point is nearly as far below sea level as planes fly above it. At the heart of the Pacific Ocean lies the Mariana Trench, a chasm so deep that if Mount Everest were dropped into it, the peak would still be submerged by more than a mile of water. The trench's deepest known point, the Challenger Deep, reaches nearly 7 miles beneath the surface, almost the same distance as passenger planes travel above the Earth. Down there, the pressure is immense, crushing enough to flatten steel. Yet even in that darkness, life endures. Strange organisms glow in the black water, thriving among mineral-rich sediments. The trench marks a subduction zone, where one tectonic plate slips beneath another and sinks back into the mantle. It is not just the lowest point on Earth, but one of the planet's great engines of renewal. It reminds us how small the visible world is compared to the vastness hidden below. The planet hums with micro-earthquakes you never feel. Even when the ground seems utterly still, it is vibrating with the faint murmurs of constant motion. Across the planet, thousands of tiny quakes ripple through the crust each day, too small for humans to detect. These micro-earthquakes release little bursts of energy as the Earth adjusts to stresses deep below. Scientists use sensitive instruments to record these whispers, creating detailed maps of shifting faults and hidden magma flows. Together they form a background hum that never ceases, the quiet pulse of a living planet. This ceaseless trembling tells geologists where faults are creeping, where pressure is building, and where volcanic systems are stirring. The stillness of the world is an illusion. Beneath every mountain, forest, and sea, the planet moves in countless small ways, sighing, cracking, and settling in slow, secret rhythms that carry the story of Earth's restless heart. Earthquakes can make entire rivers run backward. When the ground shakes with enough force, the landscape itself can change direction. During powerful earthquakes, the land can tilt or shift so abruptly that rivers are forced to reverse their flow. This rare phenomenon has been recorded in events like the Great New Madrid earthquakes of the early 19th century, when sections of the Mississippi River temporarily flowed upstream. The sudden movement of the crust can raise one side of a fault or drop another, creating natural dams or lowering valleys. For a brief moment, the power of Earth's internal forces can overcome the steady pull of gravity that guides every drop of water. When balance returns, the rivers carve new paths through changed terrain. These moments reveal the sheer strength of geological motion, showing that even something as constant and ancient as a river can be turned backward by the planet's deep, hidden forces. Some faults creep silently without any shaking at all. Not all tectonic motion announces itself with quakes or destruction. Along certain sections of faults, the crust slides so slowly and evenly that there is no noticeable shaking at the surface. This quiet movement, known as fault creep, relieves pressure in small, continuous increments. It is invisible to anyone standing above, but measurable through instruments that can detect motion of just a few millimeters per year. Some faults in California and Turkey move this way, gliding smoothly while neighboring sections remain locked and tense. The creeping portions may prevent larger quakes from forming in those regions, yet they also transfer stress elsewhere. This subtle dance between tension and release is part of the planet's constant balancing act. Even without drama or noise, the ground beneath us is shifting, whispering in slow motion as the Earth adjusts itself grain by grain across the ages. Earth's core is hotter than the surface of the Sun. At the very center of the planet lies a sphere of molten and solid metal under pressures beyond comprehension. The temperatures there reach more than 9,000 degrees Fahrenheit, rivaling and even exceeding the visible surface of the Sun. This immense heat is the leftover energy from Earth's formation, combined with the constant decay of radioactive elements deep inside. Though we will never see it directly, the core drives everything from volcanic eruptions to the magnetic field that shields life from cosmic radiation. Its motion churns like a dynamo, generating invisible lines of force that extend far into space. The inner core, solid iron, rotates slightly faster than the planet above it, while the outer layer flows in liquid form. This hidden furnace is the beating heart of the Earth, the power source that keeps our world alive with movement, warmth, and quiet resilience. There may be a whole ocean hidden deep inside the mantle. Far beneath the crust, where rock glows with heat and pressure, scientists have found minerals containing vast amounts of trapped water. These discoveries suggest that an entire ocean's worth of water may exist hundreds of miles below the surface, bound within crystal structures rather than flowing freely. If released, this hidden reservoir could fill the world's oceans multiple times over. It is not a sea in the familiar sense, but a deep, secret storage of the same substance that sustains all life. The movement of tectonic plates may carry water downward into this realm, only for it to return through volcanic eruptions and rising plumes of molten rock. This unseen cycle could be one of the keys to understanding why Earth has oceans at all. Even in the deepest stone, water finds a way to endure, waiting patiently inside the planet's mantle for eons. Crystals can grow larger than a person inside underground caves. In the quiet darkness beneath the deserts of northern Mexico lies a cathedral of crystal. The Cave of the Crystals, buried deep within a silver mine, holds translucent gypsum blades stretching more than 30 feet long. Each one took hundreds of thousands of years to grow in perfect stillness, nourished by hot, mineral-rich water that once filled the chamber. When the water drained away, the crystals remained, gleaming like frozen moonlight in the humid air. Entering the cave is like stepping into another world, one built not of rock and fire, but of slow, delicate perfection. The conditions required to create such formations are almost impossibly rare, balanced between heat, saturation, and time. These enormous crystals remind us that even the hardest materials on Earth can move and change, given patience enough. They are the planet's most beautiful expression of stillness, shaped by time. Giant gypsum crystals shimmer in Mexico's Cave of the Crystals. Deep below the surface, where heat and humidity can melt equipment in minutes, lies one of the most breathtaking sights ever found. The Cave of the Crystals, discovered by miners in the year 2000, contains gypsum formations so large they resemble pillars of light. Some weigh dozens of tons and stretch across the chamber like colossal glass beams. The crystals formed when mineral-rich groundwater remained at a steady temperature for hundreds of thousands of years, allowing molecules to arrange themselves with perfect symmetry. When the cave was drained, the growth stopped, freezing the scene forever. The atmosphere is so hot and thick that no one can stay inside for long. Yet for brief moments, explorers have walked among the shining walls of translucent stone. It is a vision of geological art, created not by hands, but by time, water, and the quiet chemistry of the Earth itself. Salt domes can pierce through rock like slow-motion explosions. In regions where thick layers of ancient salt lie buried beneath heavier rock, a strange and powerful phenomenon can occur. Over millions of years, the salt begins to flow upward, pushed by pressure from the surrounding layers. Although solid, salt behaves like a viscous fluid under great stress. It rises through the rock above, bending and breaking it, creating dome-shaped structures that can reach miles in height. These salt domes sometimes trap oil and gas, forming reservoirs that have shaped entire industries. From above, they appear as gentle swells in the landscape, but beneath the surface, they are vast pillars of slow movement, reshaping the earth in silence. Each one tells the story of ancient seas that evaporated long ago, leaving behind minerals that continue to climb skyward, proof that even solid ground is capable of flowing like a patient, unstoppable tide. Petrified wood is actually quartz, atom by atom. What looks like a fallen tree turned to stone is something far stranger and more delicate. When a tree is buried by volcanic ash or sediment, minerals carried by groundwater seep into its cells. Over thousands of years, each tiny structure of wood is replaced molecule by molecule with quartz, preserving every ring, knot, and fiber in perfect detail. The result is a fossil that still looks like wood, but feels cold and heavy to the touch. Sometimes trace elements color it in hues of red, yellow, or green, painting a natural artwork within its grain. Holding a piece of petrified wood is like holding a memory made solid, a living thing transformed into crystal by the patience of time. It is nature's way of saying that nothing truly disappears, it only changes form, keeping the story of life locked within stone. Coal began as ancient forests trapped in swampy worlds. Long before humans walked the earth, vast tropical forests covered much of the land. When these forests died, their fallen trunks and leaves sank into oxygen-poor swamps, where decay slowed to a crawl. Layer upon layer of plant matter built up, pressing down under its own weight. Over millions of years, heat and pressure transformed that buried organic material into coal, a dense rock made of concentrated carbon. Within every piece of it lies the energy of sunlight captured by plants from a prehistoric sky. Burning coal releases that ancient sunlight once more, a ghostly return of energy stored for eons. The process that created it tells a story of transformation, where life became stone and sunlight became fuel. Every lump of coal carries the imprint of ancient forests, the breath of a vanished world condensed into dark, glittering veins beneath our modern one. Oil comes from the buried remains of ancient plankton. Long before dinosaurs roamed the land, the oceans were filled with microscopic life. When those tiny organisms died, they sank to the seafloor and mixed with mud, forming thick layers of organic sediment. Over millions of years, the weight of the ocean pressed them deeper, heating and compressing them until their carbon-rich remains transformed into liquid hydrocarbons. Trapped within porous rock, these ancient molecules became the oil that powers modern civilization. Every drop we burn once drifted through a primordial sea, gathering sunlight through the simplest forms of life. In a way, the energy that fuels our world is the sunlight of Earth's deep past, stored beneath miles of stone. The story of oil is not only one of geology, but of biology, chemistry, and time, woven together in the quiet darkness below the surface, waiting for discovery. Every grain of sand tells the story of a vanished mountain. Each tiny grain of sand once belonged to something far greater. Long before it rested on a beach or desert, it was part of a towering mountain or an ancient bedrock plain. Over millions of years, wind, water, and ice ground that rock down to its smallest possible pieces, carrying them across rivers and seas. A single grain might have tumbled through glaciers, flowed down canyons, or drifted across oceans before coming to rest. Under a microscope, its shape and composition reveal the kind of rock it came from and the journey it took. Some grains still shine with fragments of quartz from ancient continents. Others are volcanic shards from fiery eruptions long past. Every handful of sand is a storybook of time, a collection of broken worlds reduced to glittering fragments that will, one day, be pressed back into stone and start the cycle again. Desert sand can sing with a low musical note when it moves. In a few rare deserts, the shifting of sand dunes creates a deep, resonant hum that can last for minutes. These singing dunes, found in places like Morocco, Chile, and the Arabian Peninsula, produce notes so pure they sound like the voice of the earth itself. The sound comes from countless grains sliding and colliding in unison, vibrating at a frequency between a cello's tone and a thunderous roar. Scientists believe the grains must be nearly uniform in size and perfectly dry for this effect to occur. Travelers describe the experience as haunting, as though the dunes are breathing or speaking. Ancient peoples often treated these sounds as mystical, believing they came from hidden spirits or gods of the desert. In truth, it is physics and friction working together, turning the landscape into a natural instrument that sings the slow, patient music of the shifting earth. Some beaches are made entirely of tiny shells. Along certain coastlines, the sand beneath your feet was not carved from stone but built by life. Over centuries, the shells of countless tiny marine creatures, such as mollusks and foraminifera, have broken down into fragments so fine they resemble powdered ivory. These biological sands can gleam white under the sun, glimmer pink from crushed coral, or even shimmer golden from the remains of microscopic algae. Each grain is a fragment of something that once lived, a piece of the ocean's past returned to the shore. Walking along such a beach is like stepping through the ruins of invisible kingdoms, where waves and tides have turned the architecture of life into a soft, shifting tapestry. The world's most famous white beaches, like those in the Bahamas and Maldives, are living evidence that time and biology can build beauty as surely as rock and fire. There are black, green, pink, and even red sands on Earth. Not all beaches shimmer with gold or white. Some are black from cooled lava, others green from olivine crystals, pink from coral, or red from eroded volcanic rock. Each color tells a geological story about its source and the forces that shaped it. Black sands often line volcanic islands, formed when molten lava met the sea and shattered into tiny glassy fragments. Green beaches appear where rare minerals from deep within the mantle wash ashore. Pink hues come from crushed shells and coral mixed with white sand, while red sands are tinted by iron-rich rock oxidized over time. Walking these colorful shores is like wandering through the palette of the planet itself. Every wave rearranges grains that carry the memory of fire, water, and time, blending the world's elements into natural art that shifts and glows beneath the ever-changing light of the sky. Glaciers carve landscapes like moving rivers of rock. A glacier seems still, yet it flows. Over centuries, the weight of accumulated snow compresses into dense ice that slowly slides downhill, reshaping everything in its path. These frozen rivers grind against the mountains, scraping valleys, polishing stones, and carrying debris for miles. When they retreat, they leave behind wide U-shaped valleys, scattered boulders, and shimmering lakes that fill their abandoned paths. The fingerprints of glaciers can be found on nearly every continent, from the smooth granite domes of Yosemite to the carved fjords of Norway. Even now, glaciers continue their patient work, grinding ancient rock into fine dust that drifts on the wind. They are sculptors of continents, artists of time and temperature, shaping the land grain by grain. In their quiet persistence lies a reminder of the planet's delicate balance, where even the coldest forces flow with a power strong enough to change the world. Some glaciers move fast enough to be seen shifting by the hour. Although glaciers usually creep at the pace of inches per day, a few flow so quickly they can be observed moving within a single afternoon. These fast-moving rivers of ice surge when meltwater lubricates the ground beneath them, reducing friction and allowing massive sheets of ice to slide rapidly forward. In Greenland and parts of Alaska, scientists have documented glaciers racing ahead at surprising speeds, their fractured surfaces groaning and cracking as they go. From a distance, the motion seems impossible. Solid ice, behaving like liquid stone. Yet this movement carries enormous power, reshaping valleys and transporting rock by the ton. As they surge, they also remind us that even in their frozen stillness, glaciers are alive with motion. To witness one in movement is to see time itself accelerate, the slow rhythm of the earth condensed into a visible, breathtaking surge. Ice under pressure behaves like slow-flowing honey. Beneath the surface of a glacier, where pressure is immense and temperatures hover just below freezing, ice stops behaving like a solid. Instead, it flows. Not quickly, but slowly and continuously, folding and bending like honey poured in slow motion. The crystals within the ice deform and slide past each other, allowing entire masses to creep downhill. This movement gives glaciers their fluid grace, their ability to carve mountains and shape valleys over tens of thousands of years. Under the right conditions, even solid rock can behave this way, flowing over geological timescales. Watching ice deform under pressure in laboratory experiments reveals how matter blurs the line between solid and liquid. What appears unyielding becomes supple with enough time and weight. The planet's greatest transformations often happen not in sudden bursts, but through the quiet persistence of materials learning to move under pressure. Fossils can capture raindrops that fell hundreds of millions of years ago. Sometimes the smallest traces of the past survive in stone. On slabs of ancient sedimentary rock, scientists have found delicate impressions of raindrops that fell onto soft mud long before humans existed. Each tiny crater records a moment in time. A storm that passed across a primeval landscape, its droplets scattering across a world filled with strange plants and early life. Within seconds, the marks were buried by new layers of sediment, sealing them in darkness until the rock hardened. When the surface is exposed again, it reveals a perfect imprint of weather from a vanished age. These fossilized raindrops remind us that even fleeting moments can last forever when preserved by chance. In a single stone, we can read the touch of a storm that ended hundreds of millions of years ago, its rhythm still visible on the pages of the planet's memory. Some fossils preserve soft tissues, even colors and feathers. For centuries, fossils were thought to capture only bones and shells, the hard remains of ancient creatures. But discoveries over the past few decades have revealed something astonishing. Under rare conditions, even delicate tissues can survive. In certain rocks, scientists have found impressions of skin, muscle, and feathers, sometimes with traces of pigment that show the original colors of dinosaurs and birds. These fossils form when mineral-rich water seeps through the remains before decay can destroy them, replacing organic molecules with stone. The result is a moment of life turned to sculpture, preserved in perfect detail. Some even retain microscopic structures that hint at how these creatures moved, breathed, and shone in the sunlight of their time. To hold such a fossil is to bridge worlds, feeling the echo of warmth and color from beings that vanished hundreds of millions of years ago. Stromatolites record the oldest known life on Earth. Long before animals or plants evolved, simple microbes built layered structures in shallow seas. These formations, called stromatolites, are the planet's oldest living fossils. They were created by mats of bacteria that trapped and bound sediment, forming domes that slowly grew toward the sunlight. Some ancient examples are more than 3.5 billion years old, making them among the earliest evidence of life anywhere. Remarkably, stromatolites still exist today in a few remote places, such as Shark Bay in Australia, where microbial communities continue their slow, rhythmic growth. Looking at one is like peering directly into the dawn of biology, when the first cells began shaping the planet. They remind us that life's story began not with motion or complexity, but with patience. Layers of living film turning light, water, and time into the very foundation of everything that followed. Earth once turned completely white during a global snowball Earth. Around 700 million years ago, our planet nearly froze solid. Ice stretched from pole to equator, sealing the oceans under miles of frozen crust and reflecting sunlight back into space. It is believed that volcanic activity, changes in atmospheric gases, and shifts in solar energy combine to trigger this global deep freeze. For millions of years, Earth remained a vast, silent world of ice, its surface gleaming white beneath a dim sun. Yet life endured, hidden in pockets of liquid water beneath the glaciers or near volcanic vents. Eventually, volcanic eruptions released enough carbon dioxide to trap heat again, thawing the planet in a dramatic, world-spanning melt. The return of liquid oceans may have helped trigger an explosion of complex life. Snowball Earth stands as one of the greatest transformations in planetary history, a near-death and rebirth written in ice and stone. Volcanoes may have ended that frozen age with a greenhouse burst. During the depths of the global freeze, volcanoes continued to erupt, pumping carbon dioxide into the air for millions of years. With the ocean sealed beneath ice, this gas could not dissolve as it normally would, so it built up in the atmosphere, trapping heat. When the ice finally began to melt, the process accelerated dramatically. Dark, exposed rock absorbed sunlight, amplifying the warming effect. Within a geologic blink, the planet shifted from frozen white to steaming blue-green seas once more. This thawing unleashed floods, erosion, and perhaps even chemical changes that nourished early life. In a way, volcanoes may have saved the planet, their quiet persistence beneath the ice keeping Earth's climate alive. What was once an age of silence became one of rebirth, proving that even in the planet's darkest cold, fire and renewal were waiting patiently below. Oxygen in the air was first made by ancient microbial mats. The air we breathe owes its existence to tiny organisms that lived billions of years ago. These microbes, ancestors of modern cyanobacteria, thrived in shallow seas and used sunlight to split water molecules, releasing oxygen as a byproduct. Over time, their waste transformed the planet. At first, the oxygen reacted with iron in the oceans, forming vast deposits of rust-colored rock. Only after these minerals were saturated did the gas begin to fill the atmosphere, slowly turning it into the life-giving mixture we depend on today. This event, known as the Great Oxidation, changed everything. It allowed complex cells to evolve and eventually made possible the rise of plants and animals. Every breath you take is a gift from those ancient microbes, whose simple chemistry turned a barren world into a living one, paving the way for forests, oceans, and all that followed. Iron formations marked the moment the planet began to breathe. In ancient seabeds around the world lie bands of red and grey rock that shimmer with metallic luster. These banded iron formations are the fossilized record of the time when oxygen first appeared in Earth's atmosphere. As primitive microbes began producing oxygen through photosynthesis, the gas reacted with dissolved iron in the oceans, creating rust-like minerals that settled to the seafloor in layers. Over millions of years, these sediments hardened into rock, capturing the breath of a newly awakening planet. Today, those same formations are mined for iron, the backbone of modern industry. Yet they began as the byproduct of microscopic life. Each stripe in the stone is a heartbeat in the planet's transformation, marking the slow transition from a world without air to one alive with oxygen, where the chemistry of life itself began to take hold across land and crow. See, there was once a time when the seas were purple. Before oxygen filled the air, Earth's oceans looked very different. The water may have shimmered with shades of red and violet, colored by ancient microbes that used molecules of sulfur, not oxygen, to capture sunlight. These organisms thrived in chemical-rich seas under an orange sky, producing pigments that tinted the water with strange hues. As photosynthetic bacteria began to release oxygen, these purple oceans slowly faded to the blue we know today. The shift from a sulfur world to an oxygen one was one of the greatest transitions in Earth's history, altering everything from the atmosphere to the chemistry of rocks. For a time, though, our planet glowed in colors we can scarcely imagine. Seas of violet under a dim sun, the signature of life experimenting with light long before the age of forests, coral reefs, or any creature that breathed air. Entire mountain ranges have vanished without a trace. The continents we see today are only the latest version of Earth's face. In deep time, entire mountain ranges have risen and eroded away so completely that no trace of them remains. Wind, water, and gravity work patiently, wearing down even the tallest peaks grain by grain. The roots of ancient mountains sometimes survive as crystalline rock buried beneath newer layers. clues left behind for geologists to find. Some of the oldest continental crusts once bore enormous ranges, now reduced to flat plains. Over hundreds of millions of years, erosion can erase a mountain as easily as waves smooth a pebble. The planet is always rebuilding itself, and what seems eternal to us is only a temporary sculpture in the ongoing art of geology. Every plain and valley was once a summit, and every stone carries the ghost of a vanished mountain in its heart. Continents have collided and split apart many times in Earth's past. Over the course of billions of years, the continents have gathered and drifted apart like slow-moving puzzle pieces. Driven by heat rising from the mantle, the crust has folded, fractured, and rearranged itself again and again. Each collision built new mountains, each separation opened new oceans. This process, known as the supercontinent cycle, has repeated at least half a dozen times. When continents collide, rocks are buried deep and reborn through heat and pressure. When they separate, new crust forms, carrying ancient fragments of lost worlds. The scars of these migrations are visible in matching fossils and rock patterns found on opposite sides of modern oceans. The land beneath our feet is not fixed, but part of a restless dance that never ends. Proof that the ground we stand on has traveled far, carrying the history of countless ancient worlds within its foundations. There have been at least 6 supercontinents before ours. Before Pangaea, before even Rodinia, the Earth assembled and broke apart at least 6 times, forming vast supercontinents that drifted through the ages. Each one had its own mountains, oceans, and climates, its own rise and fall, written in stone. Nuna, Columbia, Rodinia, Pannotia, and Gondwana are names given to these lost worlds, their remains scattered across the globe. When they existed, life was often microscopic, yet their formation shaped the chemistry of the oceans and atmosphere. Each breakup and reunion altered the course of evolution, stirring the climate and shifting the deep currents of the planet. The continents we know are pieces of those ancient giants, survivors of a cycle that spans billions of years. To study them is to read Earth's autobiography, written across time, where even the land itself is temporary and nothing stays whole for long. Pangaea was only the most recent supercontinent. About 250 million years ago, nearly all land on Earth gathered into a single vast supercontinent surrounded by a global ocean. This colossal landmass, called Pangaea, stretched from pole to pole, connecting regions that are now continents apart. Its interior was harsh and dry, far from the sea's moderating influence, while its coasts teemed with early reptiles and forests. Over tens of millions of years, heat beneath the crust built pressure until cracks appeared, splitting the land apart. The Atlantic Ocean opened, and the continents began drifting toward their modern positions. Fossils of identical plants and animals found on opposite sides of the ocean are silent witnesses to that ancient unity. Pangaea's breakup shaped modern geography and climate, setting the stage for everything that followed. It was not the first supercontinent, nor will it be the last, only one chapter in Earth's endless drift. The next supercontinent may already be forming under the Pacific. Far beneath the waves, the slow movements of the tectonic plates are setting the stage for the next great rearrangement of Earth's surface. Scientists predict that in 200 to 300 million years, the continents may once again converge into a new supercontinent. Some models suggest the Pacific Ocean will close as Asia and the Americas move together. forming a landmass sometimes called a masia. Others imagine the Atlantic closing instead, drawing Europe and the Americas toward each other. Though the outcome is uncertain, the process is inevitable. The same invisible currents that tore Pangaea apart are still at work, shifting continents inch by inch. To imagine the world that far ahead is to realize how temporary our maps truly are. The Earth is always remaking itself, and somewhere deep below, the first motions of the next supercontinent have already begun. Australia is drifting north toward Asia every single year. Far beneath the continent of Australia, the tectonic plate that carries it is slowly gliding northward at a pace of a few centimeters each year. Over millions of years, this gentle motion adds up to thousands of kilometers. Eventually, Australia will collide with the islands of Southeast Asia, raising new mountains and reshaping coastlines. Satellite measurements already track its yearly drift with astonishing precision. The motion is powered by deep convection currents in the mantle, where heat from the planet's core moves vast sheets of rock as if they were rafts on a molten sea. Though the movement is imperceptible to us, it changes maps, climates, and even ecosystems. Coral reefs grow where land once lay, deserts inch toward the tropics, and someday new mountain ranges will rise between the two regions. The continent's slow voyage north is one of the most graceful migrations on Earth. Africa may one day split into two separate continents. Deep within East Africa, a great rift stretches for thousands of kilometers, marking the place where the continent is slowly tearing apart. Volcanic activity, earthquakes, and thinning crust reveal that a new ocean may eventually form there. The East African Rift is a visible reminder that continents are never truly solid. They bend and stretch like skin over a living body. In a few tens of millions of years, the region that includes Ethiopia, Kenya, and Tanzania could separate from the rest of Africa, drifting eastward into its own landmass. Lakes such as Tanganyika and Malawi fill the rift's deep scars, early clues to the ocean that will someday flood in. Standing on its edges is like glimpsing the birth of a future continent. The process is slow beyond imagination, yet it is happening right now beneath our feet, shaping the world of tomorrow. Iceland sits directly above a tear in Earth's crust. The island of Iceland exists because it straddles the mid-Atlantic ridge, a boundary where two tectonic plates are moving apart. Here, molten rock wells upward through a long tear in the crust, building new land as it cools. The entire island is a crossroads of fire and ice, with glaciers resting beside active volcanoes. Hot springs, geysers, and lava fields testify to the restless energy below. Every few years, eruptions remind residents that their homeland is still under construction. The island's unique position makes it one of the few places where this boundary rises above sea level, allowing scientists to study the raw mechanics of plate tectonics in plain view. Iceland is a living experiment of creation, a place where the Earth quite literally grows before our eyes, balancing on the edge between the frozen North Atlantic and the molten heart of the planet. The Hawaiian Islands are a moving chain built by a stationary hotspot. In the middle of the Pacific Ocean, a plume of molten rock rises from deep within the mantle, punching through the crust to create volcanoes. As the Pacific Plate drifts slowly northwestward, each new eruption forms an island that eventually moves away from the hotspot, allowing another to take its place. This process has created a long chain of islands and undersea mountains stretching thousands of kilometers across the ocean floor. The youngest island, Hawaii, still glows with active lava flows, while the oldest islands, far to the northwest, have eroded into low atolls. By tracing this chain, scientists can map the movement of the Pacific Plate over millions of years. The hotspot itself stays fixed, while the surface glides above it, leaving a dotted record of time and motion. Each island is a chapter in an ongoing story of creation written in molten stone. Yellowstone hides one of the largest volcanic systems on Earth. Beneath the forests and geysers of Yellowstone lies an immense reservoir of magma, large enough to fuel one of the most powerful volcanic systems ever discovered. The park's steaming vents, bubbling pools, and dramatic eruptions of boiling water are surface clues to the heat below. Scientists monitor the region closely, mapping the hidden chambers that stretch for dozens of kilometers beneath the crust. Although it is not expected to erupt anytime soon, its past explosions reshaped much of North America, scattering ash across entire continents. Today, the region breathes through its geysers, releasing pressure in spectacular bursts that remind us of its inner fire. Yellowstone is both a sanctuary of beauty and a window into the restless nature of the planet, where even beneath tranquil landscapes, ancient forces of heat and pressure continue to shape the Earth in silence. Supervolcanoes can alter the planet's climate for centuries. When ordinary volcanoes erupt, they affect local weather for a few seasons. When supervolcanoes erupt, they can transform the entire planet. These titanic explosions release thousands of cubic kilometers of ash and gas into the atmosphere, blocking sunlight and cooling the globe for decades or even centuries. Evidence of such eruptions appears in ash layers and climate records from Yellowstone, Toba, and Topa. The aftermath includes volcanic winters where temperatures drop and ecosystems struggle to adapt. Though rare, these events remind us of the delicate balance between Earth's interior and its surface. The power locked beneath our feet has shaped evolution itself, sometimes triggering mass extinctions that cleared the way for new life. Yet even in their fury, supervolcanoes are part of the planet's long rhythm of renewal, cycling materials between crust and atmosphere, reminding us that life and fire are deeply entwined. The largest known volcanic eruption happened in what is now Indonesia. Around 74,000 years ago, a colossal eruption at Lake Toba in Indonesia changed the world. It expelled more than 2,000 cubic kilometers of ash and magma, leaving behind a caldera 100 kilometers wide that is still visible today. The blast darkened skies across the globe, lowering temperatures and spreading volcanic ash over continents. Some scientists believe it caused a brief volcanic winter that may have influenced early human populations. Even after the eruption ended, volcanic gases lingered in the atmosphere, tinting sunsets and cooling the planet for years. The event was so vast that it dwarfs any eruption in recorded history. Today, the tranquil lake that fills the caldera seems peaceful, but beneath its calm waters lies one of Earth's most powerful scars. A reminder that the planet's greatest moments of creation often come wrapped in destruction. Some eruptions have left ash that still circles the globe today. Fine volcanic ash can drift in the upper atmosphere for years, carried by winds that circle the planet. Particles from major eruptions such as Mount Pinatubo in the Philippines or Krakatau in Indonesia, have been detected long after the explosions ended. These microscopic fragments scatter sunlight, producing brilliant red sunsets and slightly cooling global temperatures. High above the weather, they form thin veils that reflect light in ways that painters once captured after historic eruptions. Some layers of airborne ash even return to Earth centuries later, discovered in ice cores and ocean sediments. Every eruption, no matter how remote, connects to the atmosphere that wraps the entire planet. The air we breathe today carries traces of eruptions from distant ages, a delicate reminder that even the calmest sky holds echoes of the Earth's fiery breath. Lava lakes can remain molten for decades without cooling. In a few rare volcanic craters around the world, molten rock never solidifies. These lava lakes, such as those in Erta Ale in Ethiopia and Kilauea in Hawaii, are sustained by constant supplies of heat and magma from below. Their surfaces churn and ripple like fiery oceans, crusting over only to break apart again. At night, they glow like windows into the planet's heart, their orange light flickering against dark rock and smoke. The heat balance is so precise that the lakes can persist for decades, continually refreshed by deep circulation. Watching one is mesmerizing, a living furnace breathing and pulsing in slow rhythm. They offer scientists rare insights into the chemistry and physics of magma that cannot be replicated in laboratories. Each lake is a reminder that the Earth's fire still burns just beneath its thin, cooling crust, timeless and alive. Lightning can strike inside volcanic ash clouds. When a volcano erupts, the immense friction between ash particles creates powerful electrical charges. As these charges build, they discharge as lightning bolts that crackle through the ash plume. Volcanic lightning can illuminate entire skies, creating storms of fire and light above erupting mountains. Unlike ordinary thunderstorms, these flashes are born entirely from the energy of rock and gas. Photographs capture branching bolts arcing through columns of black smoke, each strike lasting only a heartbeat but carrying immense power. Scientists study these flashes to understand the flow of ash and to track eruption intensity, since lightning can signal how violently material is being ejected. To witness one is to see the fusion of Earth's elemental forces: solid, liquid, and gas meeting electricity. A brief, awe-inspiring display that reveals how even destruction can shimmer with extraordinary beauty. When volcanoes meet ice, they create explosive steam eruptions. In places where glaciers rest atop volcanoes, heat and ice collide in spectacular ways. When magma rises beneath the ice, it melts huge volumes of water in an instant, producing steam that expands with explosive force. These eruptions can blast through the glacier, sending floods and ash clouds cascading down valleys. Iceland's volcanoes often behave this way, hidden beneath thick ice caps, until pressure builds high enough to burst free. The interaction leaves behind unique landforms, ridges and plateaus sculpted by fire and water together. Scientists call them tuyas, monuments to the strange partnership of heat and cold. Each eruption beneath ice rewrites the landscape, proving that even the most opposite elements of nature are connected in a cycle of creation and transformation that has shaped our planet since its earliest days. Entire new islands have risen from volcanic eruptions within living memory. Across the oceans, new land sometimes appears where there was once only water. Submarine volcanoes occasionally erupt with such force, but they build islands from the seafloor upward. In the past century, eruptions near Iceland, Japan, and Tonga have created fresh patches of land that still steam and harden under the sun. Some vanish again within years, eroded by waves, while others grow stable enough to host life. These newborn islands reveal the planet's creative power unfolding in real time. To watch one form is to witness the process that built continents long ago. Birds, plants, and eventually humans find their way there, turning raw lava into ecosystems. The emergence of new islands reminds us that Earth is not finished with its work. The planet continues to build, break, and begin again, renewing its surface one eruption at a time. Some lakes are filled with dissolved carbon dioxide that can erupt like soda. In parts of Africa, certain deep lakes contain massive amounts of carbon dioxide trapped beneath their surfaces. When the balance of temperature or pressure changes suddenly, that gas can burst upward in a deadly, invisible wave. Lake Nyos in Cameroon released such a cloud in the 1980s, suffocating life in nearby valleys. Scientists now monitor these lakes carefully and install systems to safely release gas before pressure builds too high. The phenomenon is called a limnic eruption, a rare but powerful reminder of how even tranquil waters can conceal immense energy. The gas originates from volcanic sources below the lakebed, seeping upward through cracks in the crust. Over centuries, it dissolves into the water like carbonation in a bottle. When it finally escapes, the result is silent and shocking. A natural event as strange as it is terrifying. Sinkholes can swallow buildings in seconds. Beneath many cities and fields, hidden cavities form where limestone or salt dissolves slowly in underground water. When the roof of one of these voids collapses, the ground above can suddenly drop away, creating a sinkhole. Some are only a few meters wide, others can stretch hundreds across, devouring cars, trees, and homes without warning. They form most often after heavy rain, when water seeps through cracks and weakens the layers below. Entire neighborhoods have been built atop such fragile foundations without realizing it. Scientists map vulnerable regions with radar and ground sensors to detect cavities before disaster strikes. Though dramatic, sinkholes are part of the planet's natural recycling of rock, where water patiently sculpts the landscape from beneath. Each collapse reveals the fragile balance between solid ground and the hidden hollows that lie quietly just below our everyday world. Karst landscapes hide secret rivers flowing through stone. Where limestone or dolomite dominates the bedrock, rainwater slowly carves intricate networks of tunnels and caverns. These underground systems can stretch for hundreds of kilometers, carrying entire rivers beneath the surface. The land above collapses in places, forming sinkholes, valleys, and jagged ridges characteristic of karst terrain. Water disappearing into a cave entrance might re-emerge miles away as a clear spring. In some regions, entire ecosystems have adapted to these lightless waterways, from blind fish to translucent insects. Karst landscapes are found on every continent and provide drinking water for millions of people. Yet their hidden nature makes them vulnerable to pollution. Exploring them is like entering the circulatory system of the planet, where stone and water move together in endless dialogue, dissolving, shaping, and renewing the surface of the Earth drop by drop. Stalactites grow from the ceiling, stalagmites from the floor, and they can meet to form pillars. Inside limestone caves, Dripping water carries dissolved minerals that slowly crystallize as it evaporates. From the ceiling, each droplet leaves behind a tiny ring of calcite that lengthens downward over centuries, forming a stalactite. Where the drops land, matching mounds grow upward as stalagmites. Eventually, they can meet to create towering columns that seem to hold the cave aloft. The process is so gradual that growth rates are measured in millimeters per century. Lantern light reveals their delicate textures. Frozen waterfalls sculpted by time and patience. These formations are living records of the cave's history, recording changes in water chemistry and climate. When viewed together, they resemble forests of stone, where every branch and trunk was born from a single droplet that fell through darkness, carrying the memory of rain and the passage of unthinkable time. Cave formations grow slower than fingernails. The breathtaking shapes found in caves are products of unimaginable patience. Stalactites, flowstones, and crystal draperies accumulate one layer at a time as water leaves behind thin films of mineral. A single centimeter of growth can take hundreds of years. The rate depends on the drip of water, the purity of minerals, and even the temperature of the surrounding rock. Some formations still glisten wet from drops that began their journey through the ground decades ago. Studying their layers allows scientists to reconstruct past climates, revealing droughts, floods, and shifts in rainfall patterns long before written history. Walking through a cavern is like entering a slow-motion clock, where time moves at the pace of minerals crystallizing. These subterranean sculptures remind us that beauty can emerge not from speed or force, but from stillness and persistence beyond human measure. Some caves have their own weather systems. Deep underground, large cave networks can develop microclimates distinct from the surface. Temperature, humidity, and airflow combine to create fogs, winds, and even tiny clouds that drift through the chambers. Warm air rising from deeper passages meets cooler air near entrances, producing swirling currents that resemble miniature weather fronts. Some caves experience regular breathing, exhaling warm air in winter and inhaling cool air in summer as outside conditions change. Moisture condenses on walls, dripping to sustain delicate formations and ecosystems. To step inside is to feel the planet inhale, the rhythm of air and rock joined together. These hidden climates preserve fossils, artifacts, and species that cannot survive elsewhere. Within their stone lungs, caves remind us that even the most solid parts of Earth are filled with movement, breath, and subtle patterns of living atmosphere. Earth's longest cave stretches for hundreds of miles underground. Beneath the rolling hills of Kentucky lies Mammoth Cave, the largest known cave system on Earth. Its passages extend for more than 400 miles, and new tunnels are still being discovered. The network was carved by ancient rivers dissolving limestone over millions of years, branching and looping in a labyrinth that could hide entire cities within its depths. Explorers move through narrow crawls, towering chambers, and underground rivers that still reshape the rock today. The air remains cool and still, and the silence is so deep it seems alive. The cave's vastness challenges the imagination, reminding visitors how much of the planet exists unseen beneath our feet. Mammoth Cave is both a geological wonder and a living record of time, carved by water's persistence into a cathedral of stone that stretches into darkness without end. Earthquakes can permanently change the length of a day. When a massive earthquake shifts the distribution of Earth's mass, the planet's rotation subtly changes. The effect is tiny, usually measured in microseconds, but still measurable. By moving enormous slabs of rock, an earthquake can slightly alter the planet's moment of inertia, just as a spinning skater speeds up when pulling their arms inward. After the 2004 Sumatra earthquake, scientists calculated that the day shortened by fractions of a second. The event also nudged the position of the poles and adjusted the shape of the planet ever so slightly. These shifts remind us that even the concept of a day, which feels absolute, is influenced by the deep movements of rock and gravity. Each quake is not only a surface event, but a planetary one, echoing through the rotation of the world itself and whispering change into the rhythm of time. Shockwaves from massive quakes travel all the way around the globe. When a powerful earthquake strikes, the energy it releases doesn't just stop at the epicenter. Seismic waves ripple outward through the entire planet, racing through rock and mantle like sound through a bell. Sensitive instruments can detect the same quake echoing around the world several times before fading. The largest quakes make the entire Earth tremble, subtly flexing its crust as energy moves from one side of the globe to the other. Even regions thousands of kilometers away can feel the faint aftershocks. Scientists use these global reverberations to map the planet's interior, tracing how the waves bend and reflect inside molten layers. Each tremor reveals something about the structure of the deep Earth, where it's solid, where it's fluid, and how heat moves within. Every great quake briefly turns the world into a single vibrating instrument, humming softly with its own heartbeat. Some earthquakes release energy equivalent to millions of tons of TNT. The scale of an earthquake's energy is staggering. When the largest faults rupture, they can release as much power as several million tons of explosive material detonating at once. The shaking that we feel on the surface is only part of it. Most of the energy travels deep into the crust, moving rock layers that weigh more than entire mountain ranges. The moment magnitude scale scientists use today was designed to measure these immense forces more accurately than older systems. During the 2011 Tohoku quake in Japan, the energy released was enough to alter the rotation of the planet and shift the seafloor by several meters. It's difficult to grasp such numbers, but each quake reminds us that the Earth's crust is under constant pressure, always storing and releasing energy in a slow, powerful rhythm that shapes continents and seas over time. Rocks deep underground can flow like putty under pressure. Though stone feels solid and unyielding to us, deep inside the Earth it behaves differently. At great depths, where temperatures and pressures rise beyond imagination, rock begins to deform slowly, flowing like an extremely thick liquid. Over millions of years, this plastic movement allows entire mountain ranges to rise, fold, and melt into new formations. Minerals stretch and twist, creating patterns seen in metamorphic rocks exposed at the surface today. In laboratory experiments, geologists have watched samples of rock bend rather than break when heated and compressed, confirming that time itself changes how matter behaves. The mantle beneath our feet constantly moves this way, its flow driving the drifting of continents above. It's a reminder that even what seems rigid is capable of motion, and that the strength of stone lies not only in hardness, but in its ability to yield, reshape, and endure. Metamorphic rocks record the history of pressure and heat inside the planet. When rocks are buried deep within the Earth's crust, they are transformed. Immense heat and pressure reorganize their minerals without melting them entirely, creating new textures and structures. Granite becomes gneiss, limestone becomes marble, shale becomes slate. Each type of metamorphic rock carries a record of the forces that shaped it, like pages in a geological diary. Scientists can read these records to reconstruct ancient mountain-building events or the depths at which certain rocks once rested. Some metamorphic formations even reveal the direction of tectonic movement through their mineral alignments. When uplift eventually exposes them at the surface, we glimpse the planet's internal history frozen in crystalline form. They are stones that remember, preserving within their folds the immense energies that flow invisibly beneath the crust, showing that every mountain once lay hidden, being rewritten by heat, pressure, and time. Slate was once mud, pressed by time into stone. Beneath ancient seas, layers of mud once settled in quiet darkness. Over millions of years, these sediments compacted under the weight of newer layers above them, squeezing out water and aligning clay minerals into flat sheets. With heat and pressure, that mud hardened into slate, a rock so finely layered that it can be split into smooth tiles. The transformation is a story of stillness turned to strength, the patience of sediment reborn as stone. Slate once formed entire seafloors. Today it roofs cottages and lines pathways, carrying the imprint of ancient oceans into our modern world. If you hold a piece and tilt it to the light, you can still see the sheen of its compressed minerals, tiny echoes of clay that once drifted lazily through water. It's proof that even the softest materials can, through time and pressure, become enduring and strong. Marble began its life as limestone filled with sea fossils. Long before it gleamed in temples and sculptures, marble began as humble limestone on the sea floor. That limestone was composed of shells and skeletons of marine creatures. Coral, plankton, and mollusks compacted over millions of years. When buried deep within the earth, it met heat and pressure that caused its crystals to grow, erasing visible fossils and creating the smooth, interlocking texture of marble. Trace minerals added subtle colors: iron for red, serpentine for green, graphite for gray. When polished, these minerals catch the light, giving marble its famous glow. Ancient civilizations prized it because it seemed to hold sunlight within. In truth, it is a relic of vanished oceans, born from life, death, and transformation. Every polished surface of marble, from a cathedral column to a carved statue, was once part of a living sea that hardened into timeless beauty. Every gemstone tells the story of its geological birth. Hidden deep in the Earth's crust, heat, pressure, and chemistry collaborate to create crystals of astonishing beauty. Diamonds form under crushing forces hundreds of kilometers down, while emeralds grow in mineral-rich veins where water and rock exchange elements. Rubies, sapphires, topaz, and quartz each arise from precise conditions of temperature and chemistry that rarely coincide. That rarity makes them precious. When cut and polished, their clarity reveals the harmony of their atomic structures, a glimpse into order forged in chaos. Gemstones travel from deep rock to human hands through volcanoes, erosion, and time. Each one is a messenger from a different environment within the planet. a record of its hidden processes. To look into a gemstone is to peer backward into the Earth's memory, seeing the patience of pressure and the art of crystallization written in perfect glittering symmetry. Rubies and sapphires are the same mineral, colored by different elements. At first glance, rubies and sapphires seem like completely different stones, but both are varieties of the same mineral, corundum. In its pure form, corundum is colorless, composed of aluminum and oxygen in a tightly packed crystalline lattice. When tiny amounts of chromium enter that structure, it glows red and becomes ruby. When iron and titanium take its place, the result is blue sapphire. Other trace elements produce yellows, greens, or even pinks. These subtle substitutions in atomic makeup change the way light passes through the crystal, giving each gem its hue. The fact that two of the world's most prized stones come from the same mineral shows how small changes at the atomic level can yield astonishing beauty. Every color is a fingerprint of chemistry, proof that nature's artistry begins in the invisible dance of elements deep within the earth. Emeralds form only under the rarest conditions of pressure and chemistry. Among gemstones, emeralds are among the most elusive. They require a perfect meeting of two very different worlds: silica-rich rocks and beryllium-bearing fluids, conditions that rarely coincide in nature. When they do, the mineral beryl forms, colored green by traces of chromium or vanadium. This delicate balance occurs only in certain mountain regions where tectonic activity has blended these ingredients. The result is a gem that carries the tension of its birth within every shimmering facet. Most emeralds contain tiny fractures and inclusions called jardins, or gardens, that mark their natural formation. These imperfections are not flaws but signatures of authenticity, evidence that the stone is a true child of the earth. To hold one is to hold the story of improbable chemistry, immense pressure, and geological patience that conspired to create something impossibly rare and luminous. Opal forms from ancient groundwater seeping through silica-rich rock. Opal is unlike most gemstones because it isn't crystalline. It forms when water-carrying dissolved silica trickles through rock, depositing microscopic spheres that stack in delicate layers. These spheres scatter light, producing opal's characteristic rainbow shimmer known as play of color. Many opal deposits began in arid landscapes that were once wet millions of years ago. As the water evaporated, it left behind these intricate, glowing structures. Under magnification, opal reveals a world of order hidden within apparent chaos. A natural mosaic of color suspended in stone. Australia, home to some of the finest specimens, was once part of an ancient inland sea where these processes unfolded. Every opal captures not only the light we see, but the memory of vanished rain, lost rivers, and the quiet chemistry that turns water and sand into fire frozen forever in stone. Meteorites on Earth tell stories from before our planet was born. When fragments of rock fall from space, they bring messages from the earliest days of the solar system. Some meteorites formed billions of years ago, long before Earth existed, from the same cloud of dust and gas that gave birth to the sun and planets. They contain minerals that have remained unchanged since that time, preserving a record of ancient chemistry. Scientists study them to learn how the building blocks of planets assembled, melted, and differentiated into cores and crusts. Some even carry organic compounds, hinting that the ingredients for life were scattered through space long before Earth began to form. To hold a meteorite is to touch something older than our world. A piece of cosmic debris that has traveled across time and distance to rest in our hands, carrying the memory of creation itself. Some rocks are older than the solar system itself. Within certain meteorites, scientists have discovered microscopic grains called presolar dust, remnants of ancient stars that existed before the sun. These tiny crystals formed in the outer layers of dying stars and were carried into space by stellar winds. Over billions of years they drifted through the galaxy, eventually becoming trapped in the material that built our solar system. Their isotopic fingerprints reveal their alien origins, differing from anything found naturally on Earth. To find such grains inside a rock is to discover stardust untouched by planetary processes, matter that predates the world itself. When we analyze these particles, we read stories written before the sun rose, the echoes of supernova and the slow breath of red giants. Each grain is a whisper from the galaxy's past, proof that the Earth itself was born from recycled stars. Lunar rocks brought back by astronauts help date Earth's early crust. The samples collected from the Moon during the Apollo missions did more than reveal lunar history. They unlocked secrets about Earth's own beginnings. The isotopic composition of lunar rocks matches that of Earth's mantle, supporting the theory that the Moon formed from debris left behind after a colossal collision between a young Earth and another planet-sized body. By studying those rocks, scientists could estimate when Earth's crust first solidified, around 4.5 billion years ago. Some of the oldest lunar basalts also record impacts that shaped the early solar system. Their surfaces, pitted by micrometeorites, have remained unchanged for eons, preserving a record of ancient bombardment lost on our eroded planet. Every moon rock brought home is a time capsule, connecting two worlds forever linked by a single violent origin story written in dust and fire. The oldest minerals ever found are tiny zircons from ancient Australia. In the ancient rocks of Western Australia, geologists discovered microscopic crystals of zircon that date back more than 4 billion years. These resilient minerals formed soon after the Earth itself, surviving countless cycles of erosion and metamorphosis. Inside each one lies a trace of uranium that has slowly decayed into lead, allowing scientists to measure their age with extraordinary precision. The zircon's composition shows that liquid water already existed on the planet when they formed, suggesting that Earth's surface cooled surprisingly quickly after its violent birth. They are among the few surviving witnesses of the planet's earliest chapter, fragments that outlasted the destruction of entire continents. To hold a zircon under a microscope is to look directly into the dawn of Earth's history, a crystal memory of a time when the world was still forming its oceans, crust, and atmosphere. These zircons record the first liquid water on Earth. Analysis of those ancient zircons revealed chemical ratios consistent with rocks that had interacted with liquid water. That discovery pushed the timeline for Earth's oceans far earlier than once thought, perhaps within 200 million years of the planet's formation. Before this finding, scientists believed the young Earth was a molten sphere for hundreds of millions of years. The zircons showed that the surface had cooled enough to sustain rain, rivers, and oceans surprisingly soon. This realization reshaped our understanding of habitability, suggesting that conditions suitable for life appeared quickly. Each zircon, smaller than a grain of sand, is a microscopic archive of water's arrival on Earth. Through them, we glimpse a world where vapor condensed, clouds formed, and the first drops of rain fell upon cooling rock. The beginning of the blue planet we know today. The continents were once covered in lava fields the size of countries. Throughout deep time, enormous volcanic events known as flood basalt eruptions blanketed vast regions of the Earth in sheets of molten rock. These outpourings sometimes continued for millions of years, forming plateaus thousands of meters thick and covering areas larger than modern nations. The Deccan traps in India and the Siberian traps in Russia are two dramatic examples. Such eruptions released immense volumes of gas into the atmosphere, altering climate and ecosystems. When they cooled, they left behind landscapes of stepped rock and rich soils that still shape agriculture today. Standing atop one of these regions is to stand upon frozen lava that once flowed in rivers of fire, rewriting continents. These fields of basalt remind us that the Earth's calm present hides a fiery past when entire regions pulsed with magma and the air shimmered with volcanic light. Those lava floods have caused mass extinctions in the past. The largest volcanic outpourings didn't just reshape continents, they reshaped life itself. The gases and ash released during flood basalt events can poison the air, darken skies, and disrupt climate for thousands of years. The Siberian trap's eruption around 250 million years ago coincided with the greatest extinction in Earth's history, wiping out most marine species and many on land. These catastrophic releases of carbon dioxide and sulfur dioxide triggered acid rain and global warming, unraveling ecosystems. Yet in the aftermath, new life eventually flourished, adapting to the changed world. These cycles of destruction and renewal are woven into Earth's long story, reminders that even the most devastating events become part of the foundation for what comes next. In every extinction lies the seed of evolution, a silent transformation written in ash and stone. Ash from ancient eruptions still lies buried in modern soils. Across the world, thin layers of volcanic ash are preserved within sediment and soil, silent records of eruptions that occurred thousands or even millions of years ago. Each layer can be traced to its source volcano by the unique chemical signature of its minerals, allowing scientists to match distant sites and build precise timelines of past events. Farmers sometimes unknowingly work these ancient ashes into their fields, their minerals enriching the soil with nutrients. In places like Italy, Iceland, and Japan, volcanic deposits have made the land extraordinarily fertile. To dig into such soil is to touch history. The residue of fire transformed into life. The same ash that once blotted out the sun now nourishes crops and forests, completing a cycle where destruction feeds creation and the remnants of catastrophe sustain the quiet persistence of growth. The Atlantic Ocean was once just a long rift valley. Before the ocean we know existed, the land that became Africa and the Americas was joined in a single supercontinent. Deep cracks began to open between them around 200 million years ago, forming a vast rift that filled with water as the continents drifted apart. Over millions of years, volcanic activity widened the gap, and a new ocean was born. The mid-Atlantic ridge, where new crust still forms today, marks the original line of separation. Ancient rift valleys like the one in East Africa offer glimpses of what the early Atlantic once looked like. Long depressions scarred by fault lines and filled with rising magma. What is now an ocean began as a fracture in the Earth's crust, proof that even immense seas start as narrow wounds in stone that slowly deepen until they become worlds of their own. The seafloor spreads outward from the mid-Atlantic ridge like a conveyor belt. In the heart of the Atlantic lies a mountain range hidden beneath the waves, where new crust is continuously formed. Magma rises through cracks, cools, and pushes older rock aside in a steady, symmetrical flow. As this happens, the continents on either side drift farther apart, carried by the movement of the seafloor itself. Magnetic minerals within the cooling lava align with the direction of the planet's magnetic field, creating striped patterns that record ancient field reversals. By measuring these stripes, scientists confirmed that the seafloor truly spreads, validating the theory of plate tectonics. The process continues at a few centimeters per year, imperceptible yet unstoppable. This underwater conveyor of creation expands the ocean even as old crust is pulled downward at subduction zones elsewhere, keeping the surface of the Earth in constant, living motion. Hydrothermal vents create black smokers on the ocean floor. Deep beneath the ocean's surface, along the ridges where tectonic plates meet, seawater seeps into the crust through cracks and fissures. It descends until it touches molten rock, heating to hundreds of degrees before rising again, laden with dissolved metals and minerals. When that superheated water bursts back into the cold ocean, it cools instantly, precipitating clouds of dark material that billow upward like smoke. These black smokers are underwater chimneys of mineral and heat, continuously forming and collapsing. They build mounds of iron, sulfur, and other compounds that shimmer faintly in the deep. Around them, the water glows faintly from reflected particles, and a strange form of life thrives, feeding not on sunlight, but on chemistry. Each vent is a miniature world, a living reminder that even in eternal darkness, the planet finds ways to breathe, burn, and build. Those vents support entire ecosystems without sunlight. Far from the reach of sunlight, life gathers around deep-sea hydrothermal vents in dense colonies. Here, instead of photosynthesis, organisms rely on chemosynthesis, a process where bacteria use chemical energy from sulfur and methane to produce food. Giant tube worms, clams, crabs, and fish all depend on these microscopic producers, forming ecosystems unlike any other on Earth. Temperatures near the vents can swing from near freezing to over 300 degrees Celsius within meters, yet life not only survives but thrives. The discovery of these ecosystems in the 1970s changed our understanding of biology forever, revealing that life does not require sunlight, only energy and water. Scientists now suspect similar environments could exist on icy moons like Europa and Enceladus. The dark ocean floor, once thought barren, hums with life powered by the planet's heat, a partnership between geology and biology still unfolding. Minerals there build chimneys taller than houses. At hydrothermal vent sites, minerals continuously precipitate from the superheated fluids streaming into the ocean. Over time, they accumulate into towering chimneys that can reach heights of more than 20 meters. These structures grow upward as long as the flow continues, layer upon layer of sulfides and other minerals forming intricate columns that resemble cathedrals in the deep. Some collapse under their own weight, only to rebuild again. Within these formations, metallic ores concentrate, the same types humans mine on land. Their shimmering surfaces host entire communities of microorganisms and animals, each adapted to the searing temperatures and chemical gradients. The vents pulse like underwater volcanoes, their chimneys smoking gently in the dark. They are proof that even in the most extreme environments, the Earth sculpts beauty from pressure and heat, crafting elaborate monuments that few eyes will ever see directly. Earth's magnetic field has flipped hundreds of times. Throughout its history, the planet's magnetic poles have reversed repeatedly, swapping north for south. These flips occur irregularly, sometimes separated by hundreds of thousands of years, other times by millions. The cause lies deep within the molten outer core, where swirling currents of liquid iron generate the magnetic field. As these currents shift, the field weakens, reorganizes, and eventually reverses. Evidence of this constant flipping is written in volcanic rocks on the seafloor, where iron minerals align with the magnetic field as the lava cools. Each stripe of opposite polarity marks a moment in this long cycle. Although a reversal could take thousands of years to complete, life has persisted through every one of them without disruption. The phenomenon reminds us that even the invisible shield protecting Earth from cosmic radiation is dynamic, a living force shaped by the movement of the planet's molten heart. During those flips, compass needles would have pointed south. If you could stand on Earth during a period of magnetic reversal, your compass would slowly begin to misbehave. Over centuries, magnetic north would drift toward the equator, then beyond it, until it pointed roughly south. These changes unfold gradually as the magnetic field weakens, splits into multiple poles, and finally re-establishes itself in reverse. Rocks preserve the memory of such shifts, their magnetic minerals frozen in the direction that was north at the time of their formation. Studying these ancient orientations has allowed scientists to trace the timeline of reversals and the wandering of poles across the planet. Though the idea might seem unsettling, reversals are natural and frequent in Earth's history. They have never caused mass extinctions or atmospheric collapse. Instead, they reveal the vitality of the geodynamo, the deep unseen engine that keeps the planet's magnetic heart beating across the ages. Even today, the magnetic poles wander by miles each year. The Earth's magnetic field is not fixed in place. The North Magnetic Pole, once located in the Canadian Arctic, is now racing towards Siberia at a speed of more than 30 kilometers per year. This drift happens because of changes in the molten iron flowing through the planet's outer core. As convection currents shift, they alter the balance of magnetic forces above. Instruments aboard satellites continuously track the pole's movements, updating navigation systems that rely on their position. While the magnetic north wanders, the geographic North Pole remains steady, making the 2 points distinct. To most people, the difference goes unnoticed, but to scientists, the shifting poles are a reminder that the field protecting our atmosphere is alive and evolving. The same invisible motion that guides compasses also reveals the slow liquid heartbeat of the world beneath our feet. The moon stabilizes Earth's wobble, which shapes long-term geology. Without the moon's steadying influence, Earth's tilt could vary wildly over time, swinging from near upright to deeply angled. Such instability would cause chaotic climate shifts, turning frozen poles into tropical zones and back again. The moon's gravity, however, keeps the planet's axial tilt stable within a narrow range. This stability has allowed long-term geological and biological cycles to flourish, providing consistent patterns for ocean currents, ice ages, and weather systems. The tides created by the moon's pull also help distribute energy through the oceans, influencing erosion and sediment movement along coastlines. Our planet's geological calm, its balance between order and change, owes much to this silent partner orbiting above. Every gentle tide and rhythmic season is, in part, a gift from the moon, which has guided Earth's dance for more than 4 billion years without missing a single turn. Tides caused by the moon sculpt coastlines across millennia. Each day, the ocean rises and falls as the moon's gravity tugs at Earth's water. Over years and centuries, these tides do more than move waves, they reshape entire coastlines. Tidal forces carve estuaries, widen bays, and carry sediments that build beaches and deltas. The gentle push and pull erode cliffs and transport nutrients that sustain marine life. In some regions, the tidal range exceeds 10 meters, creating vast intertidal zones that alternate between land and sea. These dynamic environments are nurseries for fish, birds, and countless invertebrates. Over geological time, tides have even influenced the formation of continental shelves and barrier islands. The rhythm is ancient and constant, linking the motion of distant celestial bodies to the patterns of sand beneath our feet. The shoreline we see today is a moving sculpture shaped grain by the patient breath of the moon. Coral reefs are living geological structures made of calcium skeletons. Coral reefs, though teeming with life, are also monumental geological formations. Each coral polyp builds a tiny limestone skeleton, and together, countless generations stack these structures upward toward sunlight. Over thousands of years, the result is a reef so vast it can be seen from space. The Great Barrier Reef, for example, stretches for more than 2,000 kilometers, formed layer by living builders. When corals die, new ones grow atop their remains, continuing the cycle. These structures serve as natural barriers that protect coastlines and as archives of ocean history, recording temperature and chemistry in their layers. Even fossilized reefs tell stories of ancient seas that once covered modern continents. Every coral colony is both a biological community and a geological monument, living rock that breathes, grows, and preserves the memory of the oceans that shaped our world. Some coral reefs are older than many mountain ranges. Beneath the calm surfaces of tropical seas lie reefs that have been growing continuously for tens of millions of years. Some began forming when dinosaurs still roamed the Earth. Over geological timescales, entire mountain chains have risen and eroded away, while these underwater structures quietly expanded. Their cores are made of compacted limestone formed by the skeletons of billions of tiny organisms. As sea levels rose and fell, reefs adapted, climbing upward or migrating toward the light. Fossilized remnants of ancient reefs now appear in deserts and on mountaintops, proof that what was once ocean has become land. The endurance of coral reefs shows the planet's continuity through upheaval, their layered skeletons tracing both biological and geological time. Each one is a cathedral of life and stone, older than civilization, older than mountains, a living bridge between eras of Earth's unfolding story. Dust from deserts can fertilize entire rainforests across oceans. Tiny grains of mineral dust lifted from the world's great deserts travel thousands of kilometers through the atmosphere, carried by winds across continents and seas. Much of this dust eventually falls upon distant ecosystems, where it delivers vital nutrients. The Amazon rainforest, for example, depends on phosphorus-rich dust blown from the Sahara each year to replenish its soils. Without it, tropical rains would wash essential minerals away. These airborne particles connect ecosystems that might seem unrelated, linking arid wastelands to lush jungles. Satellite images have captured vast plumes crossing the Atlantic, shimmering in sunlight before settling as invisible nourishment. Each grain is a geological traveler, a fragment of rock that left one landscape to sustain another. In this quiet planetary exchange, deserts and forests become partners in an endless cycle of erosion, wind, and renewal that spans the entire globe. Rocks on Earth contain tiny fragments of stardust. Inside certain meteorites, and even within ancient terrestrial rocks, lie microscopic grains that originated in dying stars long before the solar system formed. These specks of stardust survived the collapse of the gas cloud that birthed the sun, eventually becoming part of the material that built the planets. Their isotopic signatures are unlike anything produced on Earth, marking them as truly alien in origin. When scientists isolate these particles, they can trace the life cycles of stars, from their formation to their explosive ends. Each grain carries within it atoms forged in stellar furnaces, proof that everything on our planet, including ourselves, was once part of the cosmos. These ancient fragments bridge time and space, reminding us that geology is not confined to Earth alone, but part of a universal story of matter, transforming endlessly through creation and decay. Gold and platinum came from ancient meteor impacts. The precious metals that gleam in jewelry and technology were not part of Earth's original crust. During the planet's formation, nearly all of its gold, platinum, and similar heavy elements sank into the molten core. The metals we mine today arrived later, delivered by meteorites during a period of intense bombardment more than 4 billion years ago. These impacts scattered metallic debris across the surface, enriching the upper crust with treasures forged in stellar explosions. Every gold vein or platinum deposit is a cosmic inheritance, the residue of cataclysmic events that once lit the solar system with fire. To wear or hold a piece of gold is to touch the memory of that ancient rain of metal from the stars. It is a tangible link between celestial violence and earthly beauty, a fusion of cosmic history preserved in the veins of stone. Some impact craters are so eroded they're almost invisible. Over millions of years, wind, water, and tectonic motion can erase nearly all traces of a meteor impact. What begins as a vast circular crater gradually fills with sediment, its rim softened, and its scars hidden beneath forests or seas. Yet the clues remain in the rocks: shocked quartz, melted minerals, and buried rings of fractured crust that reveal a violent origin. Scientists use satellite imagery and magnetic surveys to uncover these hidden scars, many of which once hosted lakes or entire cities unaware of their cosmic foundation. In North America, Africa, and Australia, ancient craters have been discovered beneath layers of younger geology, some dating back billions of years. The near invisibility of these structures shows how the planet heals itself, slowly smoothing even the deepest wounds until they become indistinguishable from the land around them. One giant impact may have triggered the age of the dinosaurs. Around 200 million years ago, a massive asteroid may have struck Earth near what is now Canada, coinciding with the end Triassic extinction event. The collision released enough energy to darken skies and ignite wildfires across continents. Volcanic activity followed, and global temperatures swung dramatically. Many reptile species perished, while dinosaurs better adapted to the changing environment began to dominate. The crater left behind, though eroded, still carries traces of molten rock and shocked minerals that tell the story of devastation and renewal. Impact events like this one have repeatedly reset the course of evolution, erasing some lineages while clearing the way for others. In the wake of destruction, ecosystems rebalance and entirely new forms of life emerge. From the ashes of chaos, the great reptilian rulers of the Mesozoic rose to power, reshaping Earth's biological future for millions of years. Another may have ended it. 66 million years ago, an asteroid about 10 kilometers wide slammed into what is now Mexico's Yucatan Peninsula, releasing energy equal to billions of atomic bombs. The impact vaporized rock, ignited global wildfires, and threw enough dust into the atmosphere to block sunlight for years. Photosynthesis collapsed, food chains failed, and more than 70% of species vanished, including the Nanavian dinosaurs. The crater it left, Chicxulub, remains buried beneath layers of limestone, but perfectly preserved in shape. Beneath its rim lies evidence of immense heat and pressure, a frozen record of one of Earth's most violent moments. Yet from that extinction came the rise of mammals, and eventually humans. The event that ended one age began another, demonstrating how destruction and creation are inseparable in the story of the planet's ever-turning wheel of change. Earth's surface is dotted with hidden scars from ancient collisions. While many impact craters remain visible, countless others lie buried beneath oceans, deserts, or younger rock. Geologists discover them by studying subtle gravitational and magnetic anomalies that betray circular patterns deep below. Some of these hidden scars mark the sites of collisions so ancient that they date back to the earliest eons of the planet. In those times, Earth endured a storm of impacts that reshaped its crust and perhaps even delivered the water and carbon essential for life. These scars, though concealed, are part of the foundation we walk upon, the quiet evidence of a turbulent cosmic youth. Each discovery reminds us that our seemingly stable world has endured unimaginable violence. Over time, erosion and plate tectonics erased the marks. But deep inside the rock, the memory remains, waiting patiently to be read by those who listen to stone. Even today, space dust adds hundreds of tons of new material each day. Our planet is still growing, grain by grain. Every day, tiny particles of cosmic dust drift through space and fall into Earth's atmosphere, burning briefly as meteors or settling unseen onto land and sea. Scientists estimate that more than 100 tons of this material accumulates daily. Most of it comes from comets and asteroids shedding fragments as they orbit the sun. Collectors in Antarctica and on rooftops worldwide have gathered microscopic spheres of this interplanetary dust, their metallic surfaces glinting under microscopes. Over billions of years, such accumulation has subtly increased Earth's mass, even as erosion and the escape of gases have removed some. These particles are reminders that the planet remains connected to the wider cosmos, continuously exchanging matter with the universe around it, a gentle, ceaseless rain of stars falling upon our world. Geology links every mountain, ocean, fossil, and living thing in one story. The study of Earth's history reveals that nothing exists in isolation. The same forces that lift mountains also stir the seas, recycle rocks, and shape the conditions for life. Fossils tell how climate and geography guided evolution, while minerals record the deep processes that sculpted the continents. Every river carries the memory of erosion, and every grain of sand once belonged to stone. Over billions of years, the cycles of plate movement, volcanism, and weathering have woven together an unbroken story connecting land, life, and time. Geology is the language of that story, the script written in layers beneath our feet. It reminds us that the world is both ancient and alive, that everything we see and touch is part of an ongoing transformation, and that by studying the Earth, we are reading the autobiography of the planet itself. The rocks beneath our feet are the planet's memory, written in stone. Every pebble, cliff, and mountain is a page in the vast diary of Earth. Within their grains lie records of ancient seas, fiery eruptions, glacial ages, and the slow drift of continents. Radiometric clocks measure their ages, while fossils and mineral patterns reveal the climates and creatures that came before us. Rocks remember pressure and heat, flood and drought, creation and decay. Together, they form the grand archive of time, the evidence that the world is always in motion yet endlessly patient. Standing upon solid ground feels like permanence, but in truth, we stand atop history in motion, a crust forever forming, breaking, and reforming. To listen to the earth is to hear its long, quiet memory, the murmuring of stone recording the story of a world that has never stopped changing, growing, and remembering itself. The world beneath you is always moving. Even now, as you rest, the ground turns slowly under stars that once forged the minerals in your bones. Beneath the quiet crust, molten rock flows in endless cycles, shaping continents that drift like slow clouds across a sea of stone. Geology reminds us that change does not always roar. Most of it whispers. Mountains rise grain by grain. Oceans open wider than memory can hold. Every pebble, every crystal, every grain of sand carries the trace of time so vast that our own stories seem like brief flashes of light. Yet those flashes are part of the same pattern, written into the same fabric of the planet itself. Somewhere deep within the earth, pressure builds. Somewhere else, it eases, and a new rock begins its long transformation. Far above, wind grinds stone to dust, and that dust drifts across oceans to feed life. Everything that ever was becomes something new again. The planet breathes in the slow rhythm of stone, and we breathe with it, without even knowing. You might think of the places you have walked, the sound of gravel beneath your feet, the roughness of a cliff face, the warmth of sand between your fingers. Each is a story told in minerals, shaped by time and touch. The world is not just alive on its surface. It lives within itself, turning memory into matter, turning silence into form. As you drift toward sleep, let that thought sink in like rain through soil. Imagine the deep pulse of the planet beneath you, ancient and steady. Let it quiet your thoughts and slow your breathing. You are part of this story too. A brief moment in a vast unfolding world that remembers everything. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy. Let the planet cradle your thoughts. Still, patient, and eternal. Sleep well and good night.